Now that we know what a cache is and what its basic organization is, we're going to be going into trade-offs in cache design, which will wrap up our discussion of caches before we move into virtual memory. So there's something that we call the 3 C's of caching, and they are related to our goal, which is to minimize the AMAT, or the hit time plus the miss rate times the miss penalty. And to achieve this, what we need to do is make all kinds of trade-offs in cache organization, where we know that our main thing is to minimize the miss rate in order to really make this miss penalty less painful. So to analyze the miss rate, we're going to define 3 types of cache misses. And the first one is called a compulsory miss. And these are cold start or first reference misses. It's the first number of times that we access the cache. When at first it's empty, we're always going to get a miss. The second C, or the second type of cache miss, is capacity misses. And these are misses that are due to cache size. So a cache can often not contain all the data that the program needs. Remember that the DRAM is much bigger than the cache, so because it doesn't have a large enough capacity, it will have misses once in a while. And the third one is conflict misses. And these are misses due to mapping of several addresses to the same cache set. So if even if there is room left in the cache, but a certain address needs to map to a certain set that is already full, then we're going to get a conflict miss. So let's look at each one of these. Compulsory misses. So compulsory misses always occur after reset or cache invalidation when the stuff we have in our cache is garbage. Okay, so we cannot avoid compulsory misses. They're always going to happen. It's not something we can stray away from. But if billions of instructions are occurring, then compulsory misses are really going to be insignificant, because it's only going to be until we fill up the cache for the first time or a certain cache line. And of course, increasing the block size will reduce the compulsory misses, because we're going to be bringing in more data on each and every miss that we have, and there are going to be fewer cache lines in general. So how do we simulate compulsory misses, and how do we see how compulsory misses affect our benchmark? Well, we can set the cache size to infinity and fully associative and count the number of misses, because we're not going to have any of the other types of misses if we have an infinite size cache that is fully associative. Our next type of cache miss is the capacity misses. And capacity misses are directly related to the cache size. So if we have that infinite cache, which in this case made us not see any capacity misses, we will not have these types of misses. And larger caches, they usually increase the access time, so we can't make an infinite sized cache. Okay, so that's kind of our trade-off there. How do we simulate capacity misses? Well, we're going to change the cache size from infinity and make it smaller and smaller, and we're going to count the misses for each reduction in size. If we didn't have a cache miss when the cache size was infinite, every single cache miss that is going to be added is going to be due to capacity. The third type of cache misses is maybe the most interesting one, and that's the conflict misses. So fully associative caches allow a memory address to be stored within any cache line, and therefore we don't have a conflict miss. And that's why when we simulated cold start misses, compulsory misses, we set the cache as fully associative, because then we wouldn't have any conflict misses. However, we said fully associative caches are really expensive to use, and therefore we're going to usually use an n-way set associative or direct map cache. And n-way set associative caches only allow an address to be stored within a specific set. And therefore, if the set is full, we have a conflict miss and we must evict one of the cache lines. So the worst example is, a one-way associative set associative cache, which is called a direct map cache. And that's because each set has only one way, and we have different types of data that is mapped into the same address in memory. And so first of all, how do we simulate the effect of conflict misses? So if we change from fully associative, where we have no conflict misses, and go down to whatever n way we want, every single miss that we add is due to the change in associativity. So let's see an example of conflict misses in direct map caches. And so we have a 1 kilobyte direct map cache with 64 byte blocks, which is the example we've kind of been running with. And we're going to be running a program that all it does is it's incrementing a variable at address 0xF500. Okay, and what the program is going to do, it's going to loop between the instructions that are stored at addresses 100 and 10C, and it's going to keep on going back, and during each change between these addresses, it's going to increment the variable that's stored over here. So this is just a really kind of a made-up example, but it shows us that what we're going to be doing is we're going to keep on going to a word address, access the variable. We're going to again access the instruction memory, access the variable, access the instruction memory, access the variable, and loop back to the first instruction. And what we see is when we turn this word address in hexa into a binary, what we can see here is the set is set by these 4 bits. These are the index bits. We have, the first bunch of bits over here. The first 6 bits are the offset, and then the next 4 are going to be the index bits. And what we can see is that all of these instructions, all of these memory accesses are to the same set. And since it's a direct map cache, they can only be one cache line inside that set. And so every single time that we actually go to the next instruction, we're going to have a miss, and that's really, really horrible. And that's a type of thing that can happen in under different types of applications and different type of workloads when we have some sort of level of of conflict, some sort of level of non-fully associative caches, and especially direct map caches. So let's take what we have now and look at the basic performance of some sort of a cache. So given a base CPI, clocks per instruction, cycles per instruction, from an ideal cache, let's say it was 2 in whatever architecture we're using. And we're going to say that the instruction cache miss rate is going to be 2%, and the miss penalty for missing on any type of cache access is going to be 100 cycles. The data cache miss rate is given as 4%, a bit higher. And another thing is that loads and stores are going to be 36% of the instruction. And so if we take our pipeline over here, every single instruction, we're going to have to go to the instruction cache to pull out the program counter address from the instruction cache and go and continue through our pipe. But the data cache is only going to be accessed during load and store instructions, which are only going to be 36% of the instructions. So let's break this down. And first of all, we're going to see that the miss cycles per instruction that we're going to have for the instruction cache is that we get a miss penalty of 100 cycles, but that's only going to happen on 2% of the accesses to the instruction cache, which is going to be accessed on every instruction. So that means it turns out 2 cycles per instruction we're going to be paying for instruction cache misses. When we go over to the data cache, it's a bit different. In this case, again, we have a 100 cycle penalty, which is going to happen on 4% of the instructions, but we only access that 36% of the time, and so that's going to give us 1.44 cycles per instruction. So our total CPI is going to be our base CPI, which is 2, plus the CPI we found from instruction cache misses, plus the CPI that we found from data cache misses, and it's going to turn out to be 5.44, and that means that we got a slowdown of 2.72x, which is really bad just because of cache misses. So one of the ways to reduce the miss rate is to have multi-level caches. So what we're going to do is provide a hierarchy of caches where we see that the top over here are the inner level caches, level 1, for example, that's closest to the CPU. And as we go down in the hierarchy, we're going to get the outer level caches, and they're going to take longer to access, so it's going to take more cycles, but they're going to be larger. We don't usually go beyond level 3, and the reason is we can't actually get this, return on investment for making a larger cache versus the number of cycles it takes to access it. Sometimes we have a level 4 cache on some process, like very high-end processors, but it will often be actually off-chip in something like embedded DRAM or something like that. So you don't often see a level 4 cache on chip. Some smaller processors will only have 2 levels of caches, or older processors. And of course, if we're talking about embedded systems, they may not even have a cache hierarchy. They may just have tightly coupled memories or something like that. Okay, so we want to define something called the local miss rate, and the local miss rate is the fraction of misses at a given level of cache. So if we look at L2, it's going to have a local miss rate just of L2, and that is going to be defined as the L2 misses divided by the L1 misses. And why is that the correct thing? Because L1 misses are actually the total number of accesses that go to L2. Only things that missed on L1 will go to L2, so we can just define, L2 misses divided by L2 accesses is the same as L2 misses divided by L1 misses. The global miss rate is really the fraction of misses that go all the way down past the last level cache into memory. And so it's going to be the ln misses, like L3 or something like that, divided by the total accesses. And of course, the local miss rate of ln, which is ln misses divided by the misses to ln minus 1, is going to be much larger than the global miss rate because the total accesses is much, 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 much larger than, the ln misses. So what are design considerations for this? So first of all, L1, we're going to access it all the time. We want it to be really, really fast. We want to have a low hit time because we're going to pay for the hit time on each and every cycle. So we want to have a minimum hit time, and therefore we have to have a small cache because we cannot make a big cache as fast as we want. We'll see other reasons for that in the continuation of the lecture. So we're really going to have a small L1, but try to have as low a miss rate as we can get. So we only pay for the small hit time on every access. The small percent of accesses that go beyond L1 and miss on L1 and have to go to L2, there we want to have a really low miss rate because going off chip down to DRAM is so much more expensive than these on chip accesses that really miss rate is more important than the miss penalty, which is going to be much, much smaller than the miss penalty of going off chip. So we're going to have much larger caches, maybe larger block sizes, and possibly larger associativity to reduce the miss rate over there. So now let's look at an example of how multi-level caches performance is affected by adding another level. So if we just start with a basic one-level cache, so we have a base CPI of 1 and a clock rate of 4 gigahertz. Using this clock rate, we have a 0.25 nanosecond cycle time. We're given that the miss rate per instruction is 2%, so the L1 miss rate is 2%, and the time it takes to access main memory is 100 nanoseconds, so the miss penalty is 100 nanoseconds divided by 0.25 nanoseconds, which comes out 400 cycles on our CPU. So what we're going to do here is just going to find out what our base, CPI is with L1 missing, and we get our real base CPI of our ideal processor, and the 400 cycles that a miss to L1 gives us times the 2% miss rate, and that's going to give us a CPI of 9, which is really bad because it's 9 times slower than our base CPI of our ideal CPU. So let's add an L2 cache. And the L2 cache is going to take 5 nanoseconds to access, which is 20 cycles. So it's going to take 20 cycles to access the L2 cache, but it's a much bigger cache, and it's really optimized for miss rate. So its miss rate is much lower, and it provides us a global miss rate of 0.5%. And therefore, we can go and figure out what our complete CPI is, and it's going to be our base CPI of 1, 20 cycles, which is the access time to L2, times the local miss rate of L2, which is the miss rate of L1, right? So at 2% of the time, we're going to be going to L2. And then we're going to take our global miss rate times the amount of time it takes to access the DRAM, which is 400 cycles. So that's going to give us 3.4 CPI. Okay, and 3.4 CPI is a 2.6x improvement just by adding this L2 cache over here. Another thing that we're going to be discussing for trade-offs in cache design is the replacement policy of cache lines. We have a capacity or a conflict NISC, which means that we cannot keep the cache line that's there to bring in the other cache line. And so we have to evict one of the cache lines and bring in something else. Which one are we going to actually evict? So for a direct map cache, the answer is trivial. There's no choice to be made. We only are allowed to put one cache line in each set, and therefore we're going to evict the one that's sitting in the set that we want to fill. But once we have n-way associativity, we need to implement a replacement policy. And so we need to trade off the miss rate reduction due to a very complicated replacement policy versus the complexity of implementation, because it really can become very expensive in hardware or in software to actually do such a replacement. So there is a lot of research and a lot of things that have been done throughout the years for replacement policies, but I just want to mention a few common replacement policies. And the first kind of trivial one is random replacement, where we would randomly select a cache line to evict. And surprisingly, the performance of that is really not that bad, and it's very simple to implement such a thing. The kind of best way of doing it practically is least recently used, which means that we go and we remove the last access, the least access entry, the one that was accessed the longest time ago, and that gives us pretty good, really great performance. But it's really hard to keep track of the access order. You can think about it, but we'd have to manage all kinds of queues which show, which are the latest access, and if we have a lot of cache lines, that gets really complicated. But if we really only have two ways, so we only have two places in each set that we could have set that, we can use a single bit to implement true LRU. Every time we access a certain cache line, we toggle that 1 bit showing that this was accessed most recently, and we reset the other one's bit, so it was the older one. Pseudo LRU, or all kinds of approximate LRU, they try to go and implement LRU with different types of ways, and there's many ways to do that. One of them is doing a not most recently used. Get the just make sure that you're not replacing the last cache line or the last few cache lines that were accessed. For instance, by having a pointer that points to the latest cache line and then randomizing or something like that the cache line that you're going to evict and making sure it's not the one that you're pointing to. So that really provides us with good performance, and it's much easier to implement than true LRU. Again, there are many different implementations that are proposed, and they have trade-offs of their complexity of implementation versus how much they improve our miss rate. Another thing to discuss is write policy. So how do we make sure that the cache and memory have the same values after we've written to them? Remember, we have two copies of the same data. One's in the memory and one's in the cache. And now we're going to be writing a value. How do we make sure that the copies are kept up to date? So the first way of doing it is kind of trivial. It's doing what we call write through. So every time we read from the cache, fine, we read from it. But once we write to the cache, at the same time, we go and write to the outer level of cache. Now that is okay, but it becomes very, very slow, especially if we keep on doing writes. And so therefore, we would usually implement it with some sort of a buffer that can go, and while we can provide a bunch of writes in a row, and then while the CPU is doing other things, it can go and slowly write those into the cache. So that's kind of a type of thing to do. A write back policy writes only to the cache. And this is kind of a commonly implemented thing that we would do. We would write data into the cache, and then we would gain our best performance. And we only actually write back to the cache when we need to evict something. So when we need to evict it, we then add something that's called a dirty bit that says, since this was read from the outer level cache, we wrote to this line there. That means there is now incoherence between what we have in our cache, in our inner level cache, and our outer level cache. This is dirty, and therefore, once we're going to evict that cache line, we need to clean our cache, which means to go and write back our line into the outer level cache before we replace it. So what do we do on a write miss? And this would be probably in both cases. We are usually going to do what we call write allocate, which means that first we're going to fetch the block because we're going to need to use it. We don't just, if we write to something that's not in the cache, because of temporal locality, we're probably going to write to that again, even spatial locality, because we may write to something that's in the same line. So instead of just writing, directly to the outer level cache, we're going to first of all go and fetch that into the inner level cache and then write to that and set the dirty bit. So one more detail that it's not exactly a trade-off, but it's something that we're going to do, is add a valid bit. So when a new program starts, the data in the cache is garbage, and we need an indicator whether the tag entry is valid for this program. So what we do is we add a valid bit that's going to be 0 if whatever we have in the cache is not valid, and 1 if it is valid. So if we go in and access the cache, and even if we have a hit in terms of the tag, when the valid bit is 0, it's still going to be a miss. So there is a concept called cache invalidation, which means that we're going to reset all of these valid bits. And so when we reset the processor, we should reset all these valid bits, clear all these valid bits. But also, if we have problems with cache coherency. So, for example, if we have multiple processes or multiple processors that store different copies of the same cache line, what we're going to do is once we write to the local copy, we're going to have to tell the memory controller, go tell everybody else who has a copy to invalidate the cache line. And so what they're going to do is going to reset this valid bit. There's another concept which is called cache flushing, and I just want to mention that invalidation, flushing, cleaning, different companies, different architectures use different terminology. It gets very confusing and is very messy. So you have to make sure you know exactly what the documentation that you're talking about is doing. But in general, when we talk about a cache flush, it's when we write dirty data back to from the cache into the outer level memory, and sometimes it's going to be followed by an invalidation of the cache. I say sometimes because, again, this has many different meanings, so it's not always going to be invalidating the cache. Sometimes we just, clean the cache by writing the stuff out, but that cache line is still going to be kept valid. So sometimes we'll see in the next lecture about operating systems that when we context switch, change from process to process, then we're going to flush the cache because the cache is only good for the actual process it's been using. But sometimes there is a field that's called ASID, application specific ID, that helps to avoid having to flush the cache on each context switch because this is very expensive. And we'll see this ASID field appear later on when we discuss how these different things are implemented in RISC-V. So just as a summary of all these design trade-offs, we've seen many choices in the design of caches, so let's think about how these affect our cache. Let's start with cache size. The larger the cache, it means we're going to have fewer capacity misses. Again, we said if the cache was infinite, we would have no capacity misses, and this is good because it lowers the miss rate. The higher the cache size, the fewer capacity misses, we're going to have a lower miss rate. But on the other hand, larger caches increase the hit time, so we're going to have this rise in hit time, and so we have to trade these two things off, of course. The second issue is the block size. How many bytes are we going to have in our cache line? And so large cache lines are great because they lead to increased spatial locality. If we have, we bring in a whole block and it has the entire array that we're going to access in it, that's really cool. So it's going to reduce the miss rate, as we can see here. It also leads to shorter tags because we're going to have more offset bits, and we're going to have fewer compulsory misses, even though that's pretty negligible. But there are fewer blocks in the cache, which is going to lead to a reduced temporal locality. So really, we can get better temporal locality if we have more cache lines, and a larger block sizes is going to lead to fewer cache lines. So that's kind of counterintuitive, but it does increase the miss rate on that case. So this miss rate doesn't go completely down. It kind of shallows off. Maybe there's a sweet spot somewhere along there. And also, when we bring in larger blocks, it's going to increase the miss penalty, and so therefore that's not something that's completely trivial. And older kind of analysis of this, and it hasn't been changed until today, has found that there is this sweet spot, which is about 64 bytes, and that's why it's really a commonly used size nowadays. So what about associativity? So fully associative caches eliminate conflict misses. As we said, there are no conflict misses in fully associative caches because we can stick every piece of data, every address in any of the cache lines that we have. And that really reduces the miss rate. But they're so expensive to implement because they need so many comparators or CAMs, which are non-trivial blocks. Direct map caches, on the flip side, are much, much cheaper than fully associative caches, but they suffer from frequent conflict misses, as we saw in the example before, and therefore they increase the miss rate. There's a famous kind of a plot here from Patterson and Hennessy, which shows how, we change associativity from 1-way to 8-way and what it happens to the miss rate. And we see that really there's a big jump from going from direct map to 2-way, maybe 20 or more % reduction in miss rate. Again, this depends, on our complete architecture, on our workload and so forth, but this is kind of a good number to talk about. So that's a really important thing to do. You should probably try to use 2-way or something like that. But when we go beyond 4 to 8 ways, really we don't gain that much in our reduced miss rate, and the hit time increases, and so you wouldn't usually expect to see something more than 4 to 8 ways. We'll see later on in the lecture that that's not actually true for other reasons. Write policy is another thing, of course. Write through is really simple. It's predictable. We know exactly how long it's going to take us to access, to do a write on each thing. And it's reliable because it's not that complex to implement. But it means that we're going to write to memory all the time. And that's not good for many things, such as power perspective. Write back, on the other hand, has much lower bandwidth. We only do actually one write to each cache line, which is when we clean that out of the cache. But it's really complex to implement, and that makes it less reliable because we can easily make mistakes there and other types of things, especially when we have coherence between different caches. And it's much less predictable, of course. Replacement policies, so more intelligent replacement policies like LRU, well, they'll lead to a lower miss rate, of course, but the implementation is complex. So we have to decide what kind of replacement policy we're going to use.